Welcome to week 8, our last week. There is one remaining topic that we will talk about, and in a separate video I'll tell you about all the interesting things that we didn't get to cover, but I'll give you pointers for ways in which you can pursue them. So this one thing that we haven't yet talked about that I do want to talk about is network resilience. And this is basically the question of so far we've been nice to our networks, we've observed them and seen the fascinating properties. But in the real world, networks can be vulnerable. And it's actually rather important to understand how resilient they are to two different kinds of losses. They can lose nodes, this is node percolation, or they could lose edges, so nodes losing the ability to communicate with one another. This is edge percolation. So you want to understand how two of those two things affect how the network can function. Then we're going to look at particular topologies, namely scale-free networks, and see how random failure of nodes differs from targeted attack. That is, random failure might just occur naturally, but targeted attack, if you have an adversary, they're choosing which nodes they want to take out. So how does the network do in one scenario versus the other, and how does this depend on its original topology? And finally, we'll talk about resilience in real-world networks, and one in particular, and that is the US power grid. Let's go back to the question of whether we're removing nodes or edges. This has a mapping to lattice percolation, and you can either have here edge percolation, that is, here the nodes are these intersections, and you're just asking whether the nodes are connected via these edges, and what you're looking for is at what point does a giant component emerge. But you also may be asking, what is the path length? Because if you remember, right at the percolation threshold, these paths can be rather long. And if we're thinking about what makes a network function, it is that everyone is reachable from any other node. This has implications for information flow. But we also saw, for example, in the small world experiment, that long paths have not that high of a probability of getting the information through. So also having short path lengths between nodes is important. So we want to basically check both. The other type of percolation is node percolation, and here we've kind of switched representations a bit because each of these squares is a node and it's simply connected to the 4 closest neighbors, and now each of those squares is either occupied or not, and we're going to see what effect that has on the connected clusters. So first, edge percolation, we're going to remove each edge with probability 1 minus p, meaning that each edge is there actually with probability p, and this just is corresponding to the random failure of links. And if we want to target the attack, we're going to ask which links should we remove such that we have to do the fewest removals and inflict the most damage in terms of how much the giant component shrinks and what the average shortest path is within the component. And if you think about what strategies you might want to use, well, we've basically already done this when we were using the betweenness algorithm for community finding. Remember, the rationale there was that if we remove high betweenness edges, the removal of these edges is most likely to break up the network into communities because a lot of shortest paths went through them. So removing precisely those edges is going to most rapidly break up the network. And in a way, this percolation is actually the reverse of these attacks are the reverse of the process that we already looked at, which was adding edges, right? We started out with a fixed number of nodes, and then we added the edges one by one, and we just saw at one point, we got these small components, and then at some point we got this largish, stringy, giant component, and then the network densified from there on. And when we looked at the size of the giant component, it looked something like this, where you just don't have a giant component, and then right around average degree of 1 for each node, you get the emergence of the giant component. So now we're just doing the reverse, which is we're starting out with the network at some stage, at some density, and then we're removing the edges and we're seeing the effect. At what point does the network break up? So just to check our understanding, if you had this network here where each node has an average degree of 4.6 approximately, and you removed a fourth of the edges, and here I've highlighted a fourth, by how much would you reduce the size of the giant component? If we look at this, we can see that actually the giant component wasn't even really affected. And that is because if we remove a quarter of the edges, we drop from an average degree of 4 point something to an average degree of 3, which is still well above the percolation threshold, and we still have most of the network intact. Now let's switch over to removing nodes instead of removing edges. If you remember, we did, I think in the assignment or perhaps in the lecture, this percolation in a regular lattice, and this reminds you of water percolating through soil, which is how the problem was originally formulated, and that is if there are enough gaps, enough unoccupied sites, and these are actually going to be our nodes, in the soil, and they merge together, water can actually seep through. And at some point we're going to get to this critical threshold, at which point the water can seep through, and after that, of course, more and more water can seep through, but basically at some proportion of nodes present, the network starts to percolate. Now let's do the same thing in networks as opposed to a lattice. Here I'm showing you the Gnutella peer-to-peer file sharing network, which you have already encountered in your Small Worlds homework. And so this is, over a decade old, but one characteristic of this network is that there were a lot of nodes with low bandwidth, even some on dial-up modems, and some nodes who had high bandwidth. And so you get this hub and spoke kind of structure, and naturally, a lot of high degree nodes who are also connected to each other. So what happens if we remove a random fraction of those nodes? Well, the network actually barely notices. So here we've removed 20%, a fifth of the nodes at random, and it looks basically the same. If we look at the size of the giant component, the only thing it's really lost are those nodes that we removed. So what happened? If you look at this network, you'll realize that there are lots and lots of nodes with degree 1. And since this is just a random attack, meaning that nodes are selected at random, very likely you're going to hit the 1 degree nodes and not the few hubs. And so removing they're called leaf nodes, nodes of degree 1, because they're just kind of dangling off the network, doesn't really affect the network that much. On the other hand, if you go ahead and target nodes of your choosing, so here we've targeted the high degree nodes, you would get similar and even better results if you targeted the high betweenness nodes, but here, just for simplicity, we're doing high degree. Well, removing just the 22 most connected nodes, so that's about 3% of the nodes, and the giant component drops in size almost by a half. So why is removing high degree nodes more effective? Is it because it removes more nodes, because it removes more edges, or because it targets the periphery, that is the outskirts of the network? Hopefully what you realized is that if you remove high degree nodes, you actually remove a whole bunch of edges as well. And so you have much higher impact by removing those hubs. And here is a diagram from a paper by Rekha Albert, Havung Jung, and Laszlo Barabashi, where they studied exponential networks. So this could be the Erdős-Rényi random graph, or it could be a network that is grown randomly but without preferential attachment. And it doesn't matter if you attack with purpose or if it's just random failure, but what you see is that you start out with a giant component, and then at some point it's broken up significantly, and eventually you have mostly very small components, right? Once you're below the percolation threshold. On the other hand, the scale-free network is only going to behave like this if there's targeted attack. That is, you really need to get those hubs in order to get it to break up like this. Otherwise, with random failure, all that happens is that you keep hitting those low degree nodes just by chance, and the giant component is going to shrink modestly and eventually, shrink even more, but you'll likely have it throughout this sort of random failure process. Besides just looking at the size of the giant component, what we also mentioned matters is how many hops it is from one node to any other. What we see for the scale-free network is that if you have random failure, there's almost no effect on the average shortest path, which is good. However, the story is quite different for purposeful attack. This is where you're taking out the hubs. The average shortest path actually starts to grow significantly even while you're removing a relatively small fraction of the nodes. On the other hand, if we look at the exponential network, the Erdős-Rényi random graph, then both failure and attack have, almost no effect, just a very slight effect on the average shortest path. If we look at two empirical networks, we see this confirmed. So both the physical internet and the World Wide Web are unaffected by random failure. These are the blue squares here. And their average shortest path rises quite dramatically once you start targeting the hubs specifically.